Charging on. Okay. Charging is on. Voice clear? No, voice is clear. I can start. If voice is clear fully, I will start. Okay. Start now. Heading will be bending and shearing stresses or shear stresses sufficient. Bending and shear stresses. Remember, the most important part of strength of materials and also entire structural engineering. This is where so many people, they are having difficulty of correctly understanding. Go through all the classes with all details. You will very perfectly understand this bending stress and shear stress. Okay, start. Now, last time I started, but due to technical problem, there was a lag and class stopped after around 45 minutes, I think. So, I deleted that one. So, today is class number 1. By mistake, by habit, I put SFD, BMD, BSK. No, now it is only BSK. There is no SFD, BMD now. That course will continue in YouTube later. So, now it is pure BSK. Class number 1. See, now, first remember, you should know the most important concept in any structure. See, what I told last time in that 45 minutes, I will not tell same thing now because I don't remember what I told. But whatever I tell, subject will be same. In any structure, see, a structural member, any structural member, see, you have to add some extra statement, member, like you can write yourself only, like slab, beam, column, footing, lintel beam, staircase, anything you write, any structural member, what it will do? It will what? It will, member will, you are right here, like means you write members, will what? Will be subjected to action and reaction. See, action means, you can simple language, loading, sometimes couples also. We will restrict to loading. If I tell loading, in future remember, not only loading, even couple also is a partial type of loading only. It is called angular load, you can call. So I told in the beginning only, loading means need not be load, even can be couple. They will come from those members which our member is supporting, like beam. Beam is supporting slab. So from slab, if I am considering beam, see, if I am considering any structural member, if I consider a beam, sufficient. Furthermore, I won't tell here, because our chapter is beam only. Our beam under consideration will be subjected to loading action, that is loads transferred to beam from slab. Sometimes you will have weight wall above the beam, weight of wall, and also self weight of the beam. They are all called action. Or for the beam, except self weight, all are external. Self weight is in between. Okay, they are called action. Then there will be reaction. Reaction will be from those members to our member to maintain equilibrium, like beam supported by a column. So from column, reaction will come. So that is reaction. Further, see, these all I already told in my introduction class in SFD BMD. You can go there. And here I am not going to structural design part. So limitation is there. And remember, action together with reaction, if you consider both of them, then member will be in what? Member will be in, tell me, member will be in what? Action, reaction, both if you consider, member will be in, no, member will be in what? if you consider action, reaction both, then the member will be in, this is told thousands of times, will be in equilibrium. Okay, equilibrium, sufficient, equilibrium. So once equilibrium is maintained, remember, whatever loads are coming or applied on that member are transferred. Therefore, remember, no structural member will resist the load. It is a wrong concept. People telling beam is resisting load. If the beam is resisting the load, why you want column? Why you want column? Beam is resisting the load. No, beam will receive the load and transfer. So every structural member will perform one receiving act and transferring act. Like relay, you take from someone and give to somebody else. So loads will be transferred. But during this transfer process, see, suppose you take a beam, for example, have two simple support, will do, maybe columns. Loads are applied somewhere here, loads are spread. Load transfer will take place here. So here reaction will come. Now, your action and reaction are not at the same point. Action is spread. Reaction is at those points where supports are there. Now, this load will be transferred. But during this process, if I take cross section, see, the most important term in structural engineering, if I consider cross section of the beam, for example, imagine rectangular section. See here, imagine beam is like this. Take cross section, any cross section, then that cross section is subjected to what? Tell me. That cross section is subjected to what? Cross section is subjected to. Anybody can tell? Cross section subjected to. Cross section is subjected to. No idea? Cross section subjected to section forces. Nodi, by name only make out section forces. There are 4 types of section forces, namely 1, axial force. Briefly I am telling why all over. Second one, shearing force. Third one, bending moment. Fourth one, twisting moment or torsional moment. Now, these section forces cannot be transferred. Remember, you make a note here. Section forces cannot be transferred. Whatever SF or BM, a beam cross section will be subjected to. Beam cross section cannot tell, hey column, whatever load I am receiving, I am transferring to you. Now, my cross section is subjected to some shearing force, bending moment. Can you please take that one? Column will tell, sorry, that is your headache. That is your headache. You only transfer me loading or couples. Don't try to transfer section forces. So, the section forces right here cannot be transferred. You should write if you all understand. I will put a red line. People will tell not written. Why not written? Write it. Cannot be transferred. Instead, you can tell section forces should be what? They cannot be transferred. ಕನ್ನಡದಲ್ಲಿ ನೀನೇ ಅನುಭವಿಸು. ಹಿಂದಿಲಿ तुम्हारा प्रॉब्लम है तुम ही संभालो. They should be what? Section forces are to be resisted by cross section. By cross section, the most powerful term, by cross section. Remember, now section forces like axial force, shear force, bending moment or twisting moment, they are resisted by the cross section by what? By, anybody can tell how? By virtue of internal resisting forces or couples. That is, if you apply axial force and shear force, internal resisting force will develop. And if you apply bending moment or twisting moment, internal resisting couple will develop. You heard of the name moment of resistance? Heard of it? Heard of a term? Moment of resistance. Heard of it? Yes or no? A term called moment of resistance. Heard of it or not? Yes. Yes. They are by when the section will develop internal resisting forces. This is again resisted by due to what? Due to stresses. Remember, any section force will produce stresses. So the stresses will be resisted by cross section. So your cross section should be able to resist the stresses. Axial force, it is called axial stress or normal stress. Then shearing force, shear stresses, bending moment, bending stresses, torsion. I don't want to tell, anybody can tell. Due to torsion, if the section is circular, not rectangular, if section is circular, pure torsion, what type of stress will come? If you know it, otherwise leave it. Not our agenda here. What type of stress will come due to torsion? I told axial force, normal stress, tension, compression, shear force, shear stresses, tangential. Bending moment, I will tell you, bending stresses. And no, hoop stress. What is this one? No, torsion for circular section will give shear. So, in case of torsion, shear stress will come. It is not in our agenda, therefore leave it. Okay, now, see. When you first section force is axial force. Number one is, no, not serial number one. Axial force. Remember, I am not continuing, it can be tension or compression. How axial forces are resisted? By internal resisting forces, the stress equal to P by A, or so many things are there, simple member, compound member, then tapering member, then composite member, temperature effect, linear strain, lateral strain, so many things are there. These are all discussed in the chapter stresses and strains. That is chapter number 1 in strength of materials, which is already over for the BSK batch. Tell yes or no. Those who are in the BSK batch, it is already over. Just tell yes or no. BSK batch, stresses and strains, that is already over. Yes. Therefore, now you don't bother about axial force. Somebody who is new, he will tell, no, I am not attended. No, it is in the group. That is in the group actually. Leave it now. I decided bending and shear stress I will explain to everybody. So now, axial force over. Come to second one. That is bending moment. Third one, shear force. These two section forces, when resisted by cross section, what happens? That you are studying here. Our present chapter, bending and shear stresses. Remember, first you study bending, then you study shear. So simultaneously you are not studying. Now, right now, only bending. Once the bending reaches a stage, I will start shear, then I will tell a combined effect. So right now, for some time, it is only bending stress. See, now, that's all. Torsion will not come here. And remember, it is very powerful. Bending stresses. Bending stresses are due to bending moment. Or remember, one more is there. Bending stresses. Bending. So many places, bending is called flexure. Remember, flexure. When you take bending moment, for normal case, two types of bending moment. Do not use the word clockwise, anti-clockwise. Now I will not tell. There is a limit. Direction is not to be used. See, sagging or hogging. This way. Axial force. See, tension or compression. Shear. Twisting. This way. Okay. Now start. Now come to first bending stresses. Bending is often called flexion. Therefore, bending stress is often referred as flexural stress. Flexural stress or stress due to flexion. So I will not keep on telling every day bending or flexure, same, both are same. Okay, now first come to one by one effect. First see how bending stress will come, and then you should know how that internal resistance is developed and how equilibrium is maintained. Okay, 1 minute. See, last time what I told, this is completely different, but subject is same, principles are same, because I don't remember. If you ask me tomorrow to restart, I will tell some other way. I don't remember what I told today. See, in my class, whatever comes to my mind, I keep on telling. Fortunately, it comes correct way. Start. Now, only bending stresses, nothing else. Only bending stresses, or next time not telling flexural stresses. Now, remember, this is the beam. See, I will put time being a shape, rectangular shape. Known by heart rectangular, this is a beam. See, you apply bending moment. There will be bending, not apply bending moment, apply some loading or couples which will bend the beam. Okay, now, when you apply any general loading, see, randomly, this beam, if I put a line diagram, it will be like this. See, any random loading, beam will bend like this. You cannot see actually this one. Actually, bending is so small that deflection is very small, not visible to human eyes. If it is visible, people will not stay in the building. But this will bend. When the bending takes place this way, see, again same principle. What? As the bending takes place, there will be effect on for the fibers or for the cross section. See, I will take a cross section, any cross section here. I will take any cross section, random cross section. Okay, now see here, if the bending is this way, see here, the upper fiber here, this is called sagging beam. Sagging beam. Okay. Then anybody can tell the upper fiber, see, when it bends this way, will it get contracted or elongated? First, I will deal this chapter in a simple way. I will not go to complications, which people, if you want more knowledge, you can refer somewhere. I will not go for unnecessary complicated way of teaching. I never do it. I always ensure whatever I tell, 100% is understood. It is getting contracted, or see, it will get compressed. This will get compressed. Sufficient. You write. I wrote only comp. Some will tell, why not full? If you want to understand, write full, compressed. And see the bottom fiber here. This will get elongated or extended, or here compression will come. Here elongation means tension will come. Tension. So here at the top fiber here, compressive stress will come. In the bottom fiber here, tensile stress will come. As you take some other section, depending upon the bending moment there, the value will change, but theory will not change. Okay, now this is for sagging beam. Suppose, for example, you take a cantilever beam this way, apply any loading. See, now the beam will bend like this. Now, if I take a section here, then little slant I take, okay, no problem. Okay, no problem. Little this way, okay. Section here, then tell what happens, slightly it. The top fiber will get elongated. See, therefore tension, bottom fiber will get contracted, compression. Therefore, remember, what all I write, make a neat fair copy. Bending moment is sagging. Means, now I will do one thing. I will take a section randomly this way. 1 minute. Now here, sagging means, see, this, remember now, this is lengthwise. When you show the bending moment, your view is always lengthwise. You can, in the cross section, you cannot see bending moment. See, if you take cross section, you cannot show bending moment. Remember all these things. So, whenever I show sagging, hogging, or whenever I show BM variation, then your view should be always longitudinal or lengthwise or front view. Stand in front of beam. Never take cross section. Cross section comes for resistance. Start. So I will exaggerate now. Sagging BM. Sagging BM. So if I take here large big one, exaggerated. See. Then if the BM is sagging, if you take cross section here, upper fiber is getting compression, lower fiber will get tension. I will not explain again and again. Or if the bending moment is this way, that is called hogging. Do not use clockwise, anti-clockwise for bending. So many people, they use it. They are using because they are not knowing the basic concept. Direction is not to be used first of all. Okay, now the beam will bend like this. Exaggeration. See. Now if I take a section here, this fiber will get elongated, tension, this will be compression. Fully clear? And remember now, most important, will not tell again and again. So, the bending stresses, I will tell only once, I decided. Sometimes I tell 10-15 times. No, you go through the class repeatedly, make big note. Bending stresses, it can be tension or compression, depending upon whether you are seeing upper side or lower side here. Stresses will be always, how is the direction wise? Actually not direction. If you show an arrow mark, how will it be? How is the direction? Or how is the, see, the direction means what? See, this is horizontal, this is vertical, this is perpendicular to plane. How? Is always, tell what? Is it along the length of the beam or perpendicular length of the beam or along the length of beam or along the width of beam? See, suppose for example, you take a rectangular section of a beam to understand. Okay. This way. Oh, yo, I'm weak in 3D sketches. Okay. You take a rectangular section of a beam. Once for all settlement. Okay. This is lengthwise. This is widthwise. This is depthwise. You write fully. I am writing half. Some will tell. He is not writing full, but I am not writing full. Am I not telling it? Okay, start. Now, lengthwise, widthwise, depthwise. Tell me. Bending stress is always, answer, lengthwise or widthwise or depthwise. First. I do not want perpendicular cross section. No. I want only one word. Is it, that I will come to later. I will come to it later. Is it lengthwise? I want only one word. Lengthwise or widthwise or depthwise. Oh, okay, that is correct, but I want answer what I asked only. Bending stress is always lengthwise, widthwise or depthwise. Fast. Think a little. I am telling you, if the beam bends this way, see, if the beam bends this way, see now, a beam here bends this way, compression comes like this, tension comes like this. Therefore, how? Next time I will not tell. Is always lengthwise, breadthwise or it is always lengthwise. Lengthwise, remember. Now, itself I will tell you second concept. Now, one concept over, See, sometimes what happens is, when I change, I keep on telling, I decided this time. No, only once. If you want to mark the stress, see, show the stress, then that line is always lengthwise. Remember, compression, if this is the length of the beam, compression this way, tension this way, or lengthwise over. Now, further, this I will remove. Or, suppose you consider the cross section. I will do one thing. I will not show rectangle. I will show a random sketch, something like this. Why? See, unsymmetry I want. Remember, there is one rule. For the basic bending theory, if this is the bending moment is actually, see, now bending moment is like this. You cannot see it. You cannot, one thing I forgot now, see, when you see lengthwise here, you can see the bending moment, yes or no, sagging, or lengthwise you can see the bending moment. Tell yes or no. Lengthwise sketch, you can see the bending moment. Just tell me yes or no. Lengthwise you can see the bending moment. Clear? Bending moment can be seen. Okay, now if I write cross section, see, cut here, see here. Again I decided, only once, not 1,000 times. Only once today, that's all. The book. Okay, I want a thick book. Okay, now some Oxford, see, this is the beam. Beam is lengthwise, see, this way. See, bending moment, you can see lengthwise. But if I take the cross section, this bending moment, see now, see, I will turn the beam now. If the beam I turn here, see, this is the bending moment. In the cross section, you cannot show bending moment. Why? It is like this. Or, see here, I will show you. It is like this. This way, or see, this way. Clear? In the cross section, you cannot show bending moment. See, it is this way, or from that side, this way. Okay, now, here, in the cross section, I am marking here. Now see, the top fiber is, see here, if the bending is sagging, top fiber will be in compression. Bottom fiber will be in tension. Or, suppose, same cross section, randomly, if the BM is hogging, sagging means bottom tension, top compression. See, this sketch is perpendicular cross section. Here, it is cross section. If I take cross section here, see, here top will be tension, bottom compression. This will be tensile, and this will be compressive. Now tell me, see, I already shown you, see here, when I put lengthwise, see, compression this way, tension this way. Here, tension this way, compression this way. Because the bending compression or bending tension is always lengthwise. Now, tell me, how is it here? I will tell you, long back, I had taken a class somewhere. I asked the question. So many people told, basic knowledge we are having. Just, I don't want to tell where all I told. I asked, is the bending stress is first way, see, I will put here now. I will put a cross section here. Ask the question, is it first way, this way, or suddenly I told this way, inclined. You do not know, there were so many people who have done doctorate. People started giving, some told this way, some told this way. One person, I don't want to tell, he told, no sir, it is this way. Everything is wrong. Bending stress you cannot show in the cross section. Why? See here now. When the beam bends here, this is lengthwise. When stress comes this way, here it will come this way. Compression means this way, tension means this way. Here see, tension, both sides, tension or compression. Or when you consider cross section, when cross section is considered, remember bending stress BS, and also not only stress, also forces due to stresses. See, when compressive stress comes, there will be compressive force. Remember, bending stresses and corresponding forces are always, what tell me, I will not repeat little now, are always perpendicular to cross section. So you cannot see here, see this way, perpendicular to cross section, or instead of perpendicular, some people call normal to cross section, normal. Therefore, bending stress is always what? Bending stress is always, tell what? See, there are two type of stresses. One is called normal stress, other is called shear stress. Symbol point of view, in the BSK class, normal stress I used F, shear stress I don't know, Q I think, no. Because this is a YouTube class, I will change it, I will use normal stress because universal. 90% people follow normal stress, they take sigma, and shear stress or tangential stress, they use tau. Remember, normal stress means it is perpendicular or normal to cross section. Shear means always along or tangential, tau. Other symbols, so many people earlier in the sigma, they used to write F, and tau, some people write Q. I will stick to this one only for YouTube class. Okay, symbol is not a problem. Nobody should tell confusion based on symbol. If you want F, you write F later. Okay, sigma and tau. Now, normal stress has two types. See here, when you take the cross section anywhere, see for example, this is the cross section, normal stress, compression or tension. So when you tell normal stress, it is either normal stress sigma, that is normal stress will be either tension or compression. Therefore remember, bending stress will be always either compression or tension, or it is a normal stress perpendicular to the cross section. You cannot see it in the cross section, but you have to imagine it. See, I will tell one more thing. Later, when you draw the bending stress diagram, I will write here now. See, across the cross section. Maybe for this case, CG will come somewhere here. Don't bother. I may draw like this. I may tell sigma 1 and sigma 2. I will tell sigma 1 is the stress at the top fiber, sigma 2 stress at the bottom fiber, and I will prove that the variation across this cross section is linear. Somewhere here zero stress will come, that I will tell neutral layer or neutral axis depending on what you are referring. So many people they define neutral axis fully wrong way. What they are showing neutral axis is not neutral axis. It is a neutral layer or neutral plane. Neutral axis is different. See, concept is important. So I will prove it linear. Then see, suppose by chance you show arrow mark here. See, for example, you show compression like this. By chance, compression like this, and the tension you show like this by chance. On the same side, you can try other side, tension. Then this arrow mark or this arrow mark is not this way. It is not this way. Tell me how. This arrow mark, see, this is compression or tension. That arrow will be how? It is neither this way nor this way. It is actually perpendicular, or strictly speaking, you should draw a diagram somewhere here. See, somewhere here. Yes, then correct. Compression here, tension here. But somewhere here, you cannot write. So you fold it. So when you fold it, you write like this. When you write like this, these directions, remember, or how it is acting, that is not this way. If I show compression, it means this way. If I show tension, it is like this. So if you draw diagram side by side, bending stress diagram, you do not think that foolishly, oh, bending stress compression is this way. No, it is this way. These are all perpendicular or normal to cross section. That's all. Now I will not tell again and again. There is a limit. Fully clear? First. Full clear or not? Now I will not explain. Those people who are serious, they will understand. Those later stage, what happens is, newcomers, they get doubt. My same answer. Go to class number 1 and come. Stand in the bottom of the queue. Don't come in the queue and break the queue. There you can break. Here no. In my class, you should start from class number 1. Understand? No, I don't have time. Then don't come to my class. Okay, clear. Thank you. See, then don't come to my class. I never requested anybody that what you like the class or you please subscribe like that. No. I tell, if you subscribe, you get information. Like and dislike, you do whatever you want. I am not bothered. And first of all, I never made any request in any of my class. I never do it. Okay, now start. Now, come to bending stress. See, I will draw a cross section here. Not cross section. I will go to lengthwise here. One example sufficient. Cut. Lengthwise. Beam is going this way, lengthwise. Somewhere here, you take cross section. Then, what happens? See, suppose, imagine, to understand, BM is sagging. So, top compression, bottom tension. This will be compressed. See, you will prove later that this is maximum compression. Then, this will be in tension. You will prove that later maximum tension. Now, it's the same scale. Okay. Now, if I see here, I will put a little bigger sketch here. See, this way. See, now. See, this is compressed maximum tension. We will prove it now. Come slightly down. See, still it is compressed. It is still in compression. But the compression will increase or decrease. Tell me, using common sense. Deformation, see, here fully compressed. As I come down here, need not be down. As I come, go to other side. Is the compression will decrease or increase? First, will the compression will decrease or increase? From extreme fiber, if you come inside, it will decrease. See, it will decrease that way, lesser. If you come here, further lesser, further lesser, further lesser. Finally, you can see a plane here, where, and here see, tension. As you go this way, tension will reduce. Again, it will reduce. Finally here, a layer or plane will come. How is the plane? This way plane. See, this way plane, lengthwise. See now, I'll show how is the plane. These are all fundamentals. If you understand correctly, these are all should come to the mind. See, this way plane, or see here. If this is the beam, I will do one thing. If this is the beam lengthwise, that plane is here. See, that plane is lengthwise. That plane is lengthwise and spread widthwise. Now, that plane which is neither in compression nor in tension, anybody can tell what is that plane called? It is neither in compression nor in tension. That plane is called what? That plane or what? You can call not axis actually. That plane or layer is called name neutral plane. See, neutral plane or neutral, other one, either neutral plane or neutral, one more thing is there, neutral axle or neutral plane, or one more word I use sometimes, neutral layer along the length, layer spread widthwise. See, some, if the beam is here, somewhere here. Now, so many people tell me, they call this as what? Tell me frankly. You see classes there. So many people, they call this by mistake. What they call? In the lengthwise view, what you are seeing that neutral, majority people, not so many people, they call it what? Neutral axis. They call neutral axis. It is completely wrong. Neutral axis is something else. It is not here. See, it is a neutral plane. Now see, suppose you take the cross section now. See, cross section. I told you, upper side compression. If I hit fast, board will come out. Lower side tension. So, corresponding to this one, see here, or I will put a 3D sketch for you. See, 3D sketch for you. You can make out once for all settlement. No more settlement later. Once I explain thoroughly, next time no more explanation. See, this is, see, if I mark, if I slice here, this way, along the length, if I consider here, that is called neutral layer or neutral surface. What happened? Some sound came? Okay. Neutral, I think somebody called, I think, and disconnected. Okay, no problem. And okay. Neutral layer or neutral plane. Now, see here. In the cross section, you can see here one line. That you can see like this. See, this line is, see, this way. I will show it here for you. Only once, not 1,000 times. See, this is the beam running lengthwise. You make a note. Imagine sagging. Then upper side compression, lower side tension. Somewhere here, what you are seeing here is neutral plane. Now, if I see now, neutral plane. Now see here. If I take cross section, I can see one line here where upper side compression, lower side tension. And here, lengthwise, stresses are along the length. But in cross section, stresses are perpendicular. Anybody can tell what is name for this one? What is name for that one? First, that is called neutral axis. Neutral axis. Therefore, remember, neutral axis is line of intersection of neutral plane, line of intersection of neutral plane with what? Tell me. Line of intersection of neutral plane with what? Line of intersection of neutral plane with what? That intersection line of intersection of neutral plane with, very simple as I am showing you, with neutral axis. Line of intersection of neutral plane or neutral layer with cross section. And when you show neutral axis, you can also tell it divides the cross section into two parts. one side compression, one side tension. Which side compression, which side tension depends on sagging or hogging BM. So don't worry now. And remember that tension or compression is not along the cross section. It is perpendicular to the cross section. Last time I am telling. So it divides into two parts, cross section, two zones. One of them is called tension zone, other is called compression zone. In the cross section, this will divide into two parts. So this is the neutral axis. Little later, we will prove that neutral axis passes through what? Tell me. Little later, we will prove that neutral axis passes through. Anybody can tell? Neutral axis passes through. If you know it, tell me. We will prove it later. Little later we will prove neutral axis passes through CG of the cross section, centroid or center of gravity of cross section. Remember now, when you study bending stresses, one very important, you should know how to locate CG and how to find moment of inertia about neutral axis. In my course, I am not explaining, because it is a pre-requirement. If I start that way, this course will run for months together. So sorry, those who come here, they should know. Otherwise study. Someone will ask, reference. No, I have not uploaded any class in YouTube for CG and MI. Sorry. But for those who are in the BSK batch, tell me, CG, MI, thoroughly explained or not? Those who are in the BSK batch, CG and MI, center of gravity, moment of inertia, long back, thoroughly explained and completed or not? Long back. Just those who are in that batch. If you remember, center of gravity, because that's why the course is called basic structural knowledge. It is thoroughly explained, yes or no? Those who are in the BSK batch, you are not answering. Very thoroughly explained. Nobody is there who came to BSK batch here. So many are there. Anyway, that all if I continue here, there is no end. So my here agenda is what? Bending stress and shear stress I am covering. Any pre-requirement you should understand. So start. But maybe sometimes briefly I may tell or may not tell. Depends. If I feel good response is there, I will feel, okay, let me tell at least once or twice. If response is bad, I will tell. If you want to learn it or leave it, not my problem. Okay. Now, this is called neutral axis. Okay. Now I will go to other part now. I will remove. Now I will go to basic bending theory. Basic bending theory. Basic bending theory. Now remember, basic bending theory is always derived or considered for pure bending only. Only for pure bending. There is no impure bending. See, you should know what is pure bending. Pure bending is the bending without what? Without any. What, tell me? Pure bending is the bending without any. Without any. These are all, see, these all comes in SFD BMD chapter. This you can understand by referring to that class, SFD BMD course. Go through it. There I told you pure bending. Without any shear force, no shear stress, any shear force. And also when you take pure bending, bending moment is constant. What are the different cases of pure bending? How it will come? They all will come in the SFD BMD course. Remember, still around 80, 90 or 100 classes I am going to upload. You wait, it will come there. Till that time, believe me. Till that time you believe me. Nothing can be done. Now, Okay, now further. Now remember, therefore, see, I will take a beam, see, a beam, see, this way. Apply only end couples, say this way or this way. M and M, see. Then, if the span is L, there is no shear force, SFD, no shear force, no. BMD will be like this. It is M here, it is M here. So, entire length of beam, BM is constant. This is called pure bending. Pure bending. Or, it is possible, it can be subjected to anti-clockwise couple, clockwise couple here. Then, but both are equal, M. Then also, there is no shear force. Bending moment diagram will come this way. M. Here plus will come sagging positive. Minus you can write sagging positive. This is also called pure bending. Or if you take a cantilever beam and apply only couple M or one couple M, then there is no reaction. Nothing is there. Reacting force. BMD for both will be rectangle. Here also M. Here also M. Case of pure bending. Or suppose you take a simply supported beam, see, apply to symmetrical point load, PP, at distance of AA from here, span L, then your reaction will also come P and P. SFD will come this way, P, and BMD will come this way, PA. Now, see, A, B, C, D. AC portion, shear force is there, BM is varying. This is not pure bending. Even BD also not pure bending, but your CD portion, this portion, there is no shear force and BM is constant. This portion will be pure bending. I can give plenty of example, pure bending. Clear? These all you study in SFD BMD course. Till I reach there, till lot of class is required there. So many things are there. I will upload the classes there. Slowly I will upload. Why? Because let everybody go through 120 classes. Let them understand. Not dump everything. I will wait for some time. Then occasionally I will apply. So that once it come to mainstream, every class will be in order. Okay, now this is called pure bending. And remember, if it is pure bending, you should know that in case of pure bending, what happens is, your bending theory is M by I equal to E by R. There is one more called sigma by Y or F by Y. I will tell you, don't come now. Actually, M by I equal to stress sigma by Y equal to E by R. Sigma by Y, I will tell you, go, come later. Consider M by I equal to E by R. Or you can tell M by EI is 1 by R. Here, what is R? Tell me. Anybody can tell? What is R? What is that R? Anybody can tell if you know it? Anyway, still not proved. We will prove it. Every structural equation I will prove. Why? There is no structural equation which has proof which I am not knowing. Basic structures, not unnecessary. See, some theory of velocity, some equation I cannot prove. I am not interested. Horrible it is. Biartic principle, I don't want. Basic theory, there is no structural equation which I cannot prove if proof is there. Radius of curvature or 1 by R is called curvature. Later, when you go to deflection, we will not go here for deflection. So R is called radius of curvature of later neutral layer. So many people, they will tell neutral axis. No, it is for neutral layer. radius of curvature comes in the front view, not along cross section. Again mistake. Okay, now if EI is called, anyway, I somewhere saw EI. Anybody can tell? I think EI, I heard somewhere. Anybody know what is EI? Right now getting confused. Anybody can help me by telling what is EI? I am getting little confused now. EI, somewhere I heard it. Flexural rigidity of cross section. Okay, who told you? Oh, Parvai, Nanda Kumar told flexural rigidity of cross section. From where you got it? Oh, tell me from where you got it. I will also contact him and learn. Oh, from where you got it? Okay. Flexural rigidity of the cross section. Okay. Just for fun I told. I leave it. Just for fun I told. You know it. If I, in my class, if I tell, suppose I am getting slightly confused or wait 1 minute means people know I am playing. They know it. It is acting only. Otherwise, if I have 1 micro-millimeter doubt, I will not take the class. Okay, now, EI is called flexural rigidity of cross-section of beam. 99% people tell it is flexural rigidity of the beam. No, it is a cross-sectional property. Very sorry for them. Okay, leave it. Now, for a beam of uniform cross-section throughout, EI is constant. Therefore, you can tell in case of pure bending, M also constant. M also constant. Everything is constant. Then your R also is constant. If radius is constant, last time I told you, but that is deleted. This is I told you last time. If radius is constant, then the geometric shape is called. If radius is constant, the geometric shape is called what? If the radius is constant, the geometric shape is called. Only one geometric shape is there where radius is constant. Which one? See, parabola, cubic curve wall, if you consider, see, suppose there is a parabolic variation. If you consider some portion here, some portion here, some portion here, their radius will be different. If you imagine a small arc, their radius will be different. Radius is constant only when it is, the geometric shape is circle. Therefore, elastic curve for pure bending will be in circular shape. Circular shape means not full circle, segment actually, a part of circle. See, if circle is like this, elastic curve, see, or if the elastic curve is this way, if you continue, you should get what? Suppose imagine, this is the elastic curve. Imagine, elastic curve. This is a real elastic curve. See, now, if I continue, you should get what? If I continue full, all round, you should get what? If I continue, you should get. If I continue the elastic curve, you should get what? You should get a circle. Circle of constant radius R. Okay, now, there are some assumptions in basic bending theory. I will dictate here. These all you have studied from books or anywhere. See, one, the first assumption, if you want, I will give clarification, not now, after the equation is derived. Because if you want a clarification for that exam assumptions, you should know why it is valid. This, so many people, everybody almost know it. Why? Studied for examination. But with the regret I should tell, majority are not knowing what it means. Anybody can tell what is that one? Majority are not knowing what it means. If I ask you, okay, tell the meaning of the assumption. Sir, meaning the Kannada, gottilla, or Hindi, pata nahi. Then, why you know it? Sir, studied for examination. Anybody can tell what is that one? Anybody can tell what is that assumption which needs very delicate what? Observation. Anybody can tell? Starting of that assumption. Very delicate observation. 99.99% people, I am not telling 100%, maybe 1 in a lakh will explain correctly what is the meaning of that assumption. Anybody can tell the starting word for that one? Starting word for that assumption. Nobody knows. You know it. Tell me. If you don't know, tell don't know. I will tell it. If you don't know, tell don't know. The starting of that assumption. No, not that one. That everybody knows. Material is homogeneous, isotropic. That's all. We see, in every theory we assume material is homogeneous, isotropic. Not that one. The assumption is, see, one, plane section before bending. Plane sections before bending remain plane after bending. Remain plane after bending also. After bending also. Tell me yes or no. That is, see, before bending you can see a plane. After bending, curvature will come. Even if curvature will come lengthwise, but cross section wise, no curvature. See, no curvature. It will remain in one plane. Plane section before bending, remain plane after bending. Tell yes or no, fast. Yes, this is the assumption for which 99.99% will not answer properly. If they answer, if anybody answers, I can easily trap them. Okay, maybe 1 in lakh, I agree. I may not be able to trap. I will appreciate, I will tell, yes, good. You know the principle. Good. Okay, let's chart continue. Very, very rare case. Okay, now see, this I can explain further only after we go little further. After knowing the effect of the stresses only I can discuss. The strain etc. are required. So time being, you leave it. Hey, go. One. Now, further assumptions, so many are there. You refer, I don't know how many are there. One by one I will tell briefly if I remember. Modulus of elasticity is same in both compression and tension. Okay. Now, you should listen to me and write. And the loading is such that member is strained or stressed within proportionality limit or simple language elastic limit. Fourth one, there is no resultant thrust for cross section. There is no axial force there. So compression tension coming is only due to bending. 5, there is no shear force. Bending is pure bending. Then something he told, material is homogeneous and isotropic. Further, I don't remember. An idea? Further, I don't remember. Not required. If you want, refer some 3-4 books, take from them and make a list. So don't expect me to waste time on such things here. Anybody can get. Nowadays, see, Google. You Google, you Google today. Yes, basic bending theory assumptions. This will come. You write clarification. Some clarification will come. I am sure that is not complete. Okay, now, these are your problems. This theoretical portion, usually I don't discuss too much of theory portion. My principle is always pure, I want to bring it to pure mathematical format. Okay, start. Now, consider basic bending theory. Okay, 1 minute now. See, consider a beam. See, this is the beam. You should, now I am going for derivation. Derivation I am going. See, consider a beam this way, subjected to say end couple M here, end couple M. Tell me, this couple is clockwise couple or anti-clockwise couple? Fast. If I see from this side, this couple is clockwise couple or anti-clockwise couple? Fast. One more thing. Thank you. Mr. Sridhar Murthy told one more thing. Element to allowed, each fiber is allowed to expand freely independently of the adjoining fiber. When one fiber gets compressed, see, adjoining fiber, it will not affect. So, correct, thank you. Each fiber is allowed, it is free to expand or contract independently. Thank you very much. See, these are all assumptions you take. Thank you very much. One more given there. You see comment box, it is there. See, Mr. Sridhar Murthy told, you copy down, 100% correct. Section remain plane over. Bending assumed is plane even after bending. Okay. Plane. Okay. Then one more is there, I will tell later about the axis. See, one more is that the cross section is symmetrical about the axis perpendicular to neutral axis. See, if this is the cross section, this is neutral axis, it can be unsymmetrical. See, it should be it should be symmetrical about this one. So you can solve even for T section also. Why? Symmetry. You cannot solve for angular section. This will become unsymmetrical bending. So basic bending theory you cannot apply. Suppose you call this as x-x axis, there should be symmetry about y. That is very important. Otherwise it becomes unsymmetrical bending. Shear center all will come. Regarding shear center, I have an idea to update a course. Very beautiful chapter, shear center. So very important for higher studies. I am in two minds. Shall I update a course separately when I am free only for shear center, or later? I decided not now. Right now my classes people are viewing, but that huge number they are not viewing. A time should come when I upload a class, huge number, they should wait for the class. Then I will upload. Better I will wait till people start coming more and more to my class. They should realize, yes, there is a class in the YouTube here where you get infinite knowledge. Once that stage comes, then I will start. Okay, now see, you are not answered the question. Is this couple clockwise or anti-clockwise? See, is this couple clockwise or anti-clockwise? Still you are not answered the question. Tell me fast. Is that couple clockwise or anti-clockwise? A person in YouTube was telling it is not called couple. He is calling it is called concentrated moment. He tells couple means, he will tell this is called couple. Let him come in front of me. Within no time he will go back and tell in his class, sorry, this also is couple. I will see that when he leaves me, talking with me, next day he will tell, all these days I told this is concentrated moment, this is called couple. Now something happened, sorry, you can call this also couple. He very sorry, basic idea is not there. He is insisting, this is not couple, this is not couple, not couple. I used to laugh. When I listen, I will laugh for his ignorance, that's all. When somebody is ignorant, does not know something and tells my point is correct, others are wrong, that means you can laugh. But if someone knows correctly, he will not tell those things. You are still not answered. Is this, you should answer, otherwise I will terminate the class. Is this couple clockwise or anti-clockwise? Fast. Abbabba. Yarri adu? Yaru? Nandakumar. Nimma watch. Is this anti-clockwise, clockwise? This is anti-clockwise for you. Iri. 12, 6, 3, 9. My watch is turning this way. I don't know. Is your watch turns this way? Is this couple clockwise or anti-clockwise? No, I am not talking about bending moment. See, This is what happens in my class. If I ask a question, people are afraid. I am not talking about bending moment. I am considering moment, action. I have still not told bending moment. This is clockwise. Someone with the courage typed there. Thank you. Yaru? Oh, got it. Got it. I know. Clockwise. This couple is anti-clockwise. Now, if I take a section here, if I look this side, tell the bending moment. Bending moment, M. If I look this side, any section, bending moment equal to M. Tell me, M, sagging M or hogging M? If I look this side, sagging M or now it is bending moment. Now you should not use clockwise, anti-clockwise. It is M sagging. Or if I look that side, then also bending moment equal to M only. This side you got sagging, but that side it is what? Tell me. Left side you got sagging, but right side you got what? Left side you got sagging, right side you got right side also sagging. See, this also, first of all, waste of time. SFD BMD course I told you, when you are discussing bending moment, you remove your watch and what? Remove the watch and throw it outside. Do not use the watch. You see only bending nature. See, whether you see left side or right side, this bending moment is sagging. Correct. Or if therefore any cross section, the bending moment diagram is like this. M here and M here, full positive, sagging positive. Or this beam, any section cross section, it is subjected to what? Tell me, what bending moment? Subjected to pure bending. Subjected to pure bending. Clear or not? Subjected to pure bending. Clear now? Subjected to pure bending. Clear or not? Fast. Subjected to pure bending. Why? BM is constant. Why no answer? Clear? Okay. Now do one thing. Continue further. Continue further. Now, for this beam, I will write somewhere here. See, little lesser dimension. This way. See, beam actually is like this. Very small. See, here M, here M, M. You take two sections very, very nearby. Actually, infinitely small. Infinitely small. Can you tell me what is the distance you are using? Suppose this way I measure X, this way I measure Y, infinitely small. Tell what I am using. I can't call X. What it is called? Along X, infinitely small distance is called mathematically what? Infinitely small distance length, along length is called delta XLR, dx. This d is not the depth d. Remember, rectangle, you tell b by d. This d is the depth d. This is mathematical. That much. Some people call delta. No, I want dx. Element length dx. Actually, remember now. Actually, it is so small. It is like this. See, this way, very, very small. Now, beam will bend like this. Bend like this. Now, this point, see, last time I numbered, named. Now I do not know what way I named. You can tell, sir, last class you wrote A, B, C, D here. That is deleted class. I don't remember what comes to my mind. I will call this is A, this is B. See, usually A, B here. Don't see that one. This is C, this is D. And somewhere here, there will be neutral layer. I will call EF. Remember. And EF I will use red color. EF, I will use red color now. EF. EF. Then here, see, your AB, tell me, these two sagging BM. So upper side compression, lower side tension. Therefore, A and B after bending, see, if I project those points now, see, this way, A and B after bending will move inwards or outwards first. A and B will move inwards or outwards first. Inward or outward. A and B will move inward or outward first. Little part. They will move inward. So your A will go to position A dash, B dash. Tell me, is AB more or A dash, B dash more? First, tomorrow's class I will tell all those who are coming new today, I am not responsible for any misunderstanding. You should study class number 1 and join. Or when you came here, continue. But do not put any blame on me. I will not be, first of all, I am not responsible for anything. But still, ethics point of view, I will tell, nobody can put any blame on me. This is not clear. Class number 1, then come to class number 2. Don't come to class number 2 direct. If you came, attend the class. Little you understand. When later, any day, after 10th class, someone comes and tells, sir, not clear. Class number 1. I will tell, class number 1, come from there. No time. Leave. Don't come to my class. Over. Tell me now. This I will not tell tomorrow. A dash, B dash. Will it be more than AB? See, this way, you go to any person who derives basic bending theory. Tell frankly, will anybody will give you this much details? Tell frankly, this much details. Can you imagine somebody giving, if yes means tell yes. This much details for bending theory or all important concept. If anybody gives, okay, tell no problem. I want to know who is giving. If this much explanation and in principles, then okay. But I know nobody has got that much patience. By this time, they will finish the bending theory derivation as seen in YouTube, bending theory derivation, and also that M by I, sigma by Y, E by R, show that it passes to neutral axis, and then moment of resistance, assumptions, and then 1 or 2 problems. Sometimes they finish in some 20 minutes class or 25 minutes class. Now it is approaching 9 o'clock. Still I have not started bending theory. I am still struggling to convince you. So remember, tell me, these all you should make a note. Tell the answer. Is that A dash B dash is more than AB or less than AB? First. See, now here, here, if I see, this is the original. In the original, that is before bending. Tomorrow I am not explaining. Before bending, your AB equal to CD equal to EF equal to DX. Tell yes or no. In the before bending, see, AB equal to CD equal to EF. Tomorrow I am not telling once again. Why? Limit is there. The red color is gone now. It is not writing. Okay, EF. Okay, red is not writing. I will put black color. Half red is there. EF. Your EF. See, this is D. AB equal to EF equal to CD equal to DX. Tell yes or no first. Tell yes or no. AB equal to CD equal to EF equal to DX. Tell yes or no. Okay, now tell here. I am not comparing there. Now this is A dash B dash. This is C dash D dash. Somewhere here we have E dash F dash. Sorry. Somewhere here we have E dash F dash. Tell the answer. Now, I want to compare after bending. After bending, tell correctly. See, if you understand this way all the basic concept and one or two examples numerical with perfect basic, see where you stand later. You will be king for this theory. You will tell anybody, bending theory, you ask whatever you want. Okay, start. I want to compare here now. Your A dash B dash, is it more or less the after bending? Your A dash B dash, is it more or lesser than AB? First. I want only compare with original. I want less or more. Your A dash B dash is less than or more than AB. Is less than AB. AB. Okay. Whereas your C dash D dash is what? Tell me. Your C dash D dash is bigger. It is more or lesser. C dash D dash is more or lesser. You should, what Nanda Kumar wrote is correct, but I want the deformed shape first is more than C dash CD. Correct? See, very simple. Tell why. Think a little. This is going to be get compressed. See, I told you, upper fiber compression, lower fiber tension. Then only you can make out. If compression, it will contract. It will contract, length will become lesser. In tension, it will expand, this will become more. Now tell me, same way, if you compare EF with E dash F dash, tell your, this way, E dash F dash is more than EF or less than EF. First, this is a closing part now. Today's closing part. E dash F dash is more than EF or less than EF. It is equal. Tell why? Because it is neutral. Clear or not? Because it is neutral. It is neither contracting nor elongating. There is neither compression nor tension. It will remain same. First, clear. Or further equal to what? So your E dash F dash is also equal to what? Tell me. E dash F dash equal to EF. Therefore, your E dash F dash is further equal to what? Last statement today. It's also equal to dx. Over. That's all. Already 9 p.m. and I'm talking non-stop without any break for 1.5 hours. See, usually I take some small break, 5 minutes. Today I have not taken the break because I do not want to break that trend or what you call, I don't know some word. Sometime I won't able to find the word for that one. That flow, I don't want to break the flow, so I will stop now. And very important, see, when I continue tomorrow, next class is tomorrow only, I will write length of AB will reduce to A dash B dash. CD will increase to C dash D dash. EF will remain same as E dash F dash. So, E dash F, if I take any length here, E dash F dash length equal to EF equal to dx. Or, if I take any other fiber here, then originally that length equal to dx, finally it will deform and change. If that fiber is above the axis, I will tell length will reduce. If it is below the axis, I will tell length will increase because it is sagging BM. If it is hogging BM, upper side anywhere you consider, length will increase, lower side anywhere you consider, length will decrease. That I will not repeat tomorrow. Those who are coming new for tomorrow, first I give the warning. You go through class number 1, then only understand correctly. Clear? If clear, I will stop the today's class now and continue tomorrow now. See, 1.5 hours, I talked only about the important basic concept. They are all somewhat mathematical. I never talked any material property. See, I talked only about the real bending, how it comes, or because of bending, what is the deformation effect I told today. And also I told you, bending moment you can show lengthwise, bending stress also lengthwise. When you take cross section, you cannot show stresses. Stresses are perpendicular. One side compression, one side tension. Lengthwise neutral layer or neutral plane in the cross section is neutral axis. Okay. Full clear? What all I told, full clear? Those who want a thorough knowledge, even if you came today, it is better after dinner, say 10 o'clock or 11 o'clock, once again go through the class. You will not lose anything. You will keep on gaining only. Remember, again and again go through the class, so that by going to class again and again, 100% you will not lose. You stand to gain only. Clear now? Okay, tempo. See, sometime in English, I won't be able to get a correct word. I am not regretting. Why? Those are called what? Style or what you call is impression all. I do not want such impression. See, people tell this way. See, now, AB compression. Therefore, be careful. Such language I never use. Tell simple language like day-to-day life. So people understand. Stylish language, you go for speeches only. Okay, thank you. Tomorrow we will continue. Already feeling too tired. No. That I will surely explain. Don't worry. I will surely explain. If not here, in the BSK class. Because I will decide. There are so many finer points are there. Therefore, sometimes I feel I will explain to my students, not general public. Not that I don't want them to know. No, special provision for those who came to my class. You make a list. Anything you ask, I will tell. No problem. If I do not know the answer, I will not talk about anything. See, so far, I never asked a question, single question, without knowing answer. Without knowing answer, I never asked a single question. Okay, thank you. I will go to the class.